Okay. So I'd like to introduce the final speaker of the vehicle electrification section. His name's Rahul Mangharam. He's from the University of Pennsylvania, and also has a small research venture startup called Autoplug that he's forming. And his talk is titled The Car in the Cloud, Remote Automotive Electronic Controller Unit Diagnostics, Testing, and Reprogramming.
Hi. Thanks for having me here. So I thought I'd like to just start by echoing some of Professor Alan Taub's comments last night in terms of how the effective efficiency of your car today is in the range of about 5 to 6%. And of that, really, what really brings it all the way down or can lift it up, a significant factor really is with the vehicle controls. So the vehicle controls determine a significant part of the efficiency of how your battery is used, whether you can recover 90% or you're recovering something like 65% of your fuel efficiency at the source. And the second thing is really controls really also have become the predominant sort of approach to actually providing you safety in your car. And so that's what I'll talk about over here today is really let's look at the intersection of the controls, the communication, and the computation that are very tightly coupled with your physical bucket of bolts as we know of it or think of it today. And so that's why we think of this as a cyber-physical system where we have this constant interaction. And so I'll start with really looking at what are the concerns within the vehicle and really looking at the control software specifically and why we should care about that and why it's become actually one of the growing and major problems in automotive recalls management. Then we'll bubble up one step further out of the vehicle where today all your safety is really built in into the body of the vehicle. You have your crash sensors, you have your range finders, you have your rear view cameras, and so it's really forming a bubble around your car of a safety bubble. But now the idea is that what if we can now have vehicles talk to each other and expand that bubble to be a networked active safety. So if there's an accident up the highway, you can transmit this message within 500 to 700 milliseconds and alert people early on. And what other capabilities? So I know within GM, Toyota, Ford, all the top companies are really looking at, well, can we do telematics? What sort of telematics would we use? And then we go one level even further out after that to look at very large-scale traffic congestion systems and how we would actually look at the eastern routes or the West Coast traffic congestion routes and how we can do real-time traffic congestion management and do real-time, very responsive, fastest path assignment to all drivers in a closed-loop manner. And so we go from one vehicle to maybe a couple of hundred to thousands of vehicles to millions of vehicles. And so we'll start from one vehicle. And so a lot of this work is done in this university transportation research program with the DOT between Penn and CMU. So let's look at in-vehicle systems over here. And so essentially what we are really interested in, if you look at a car today, before the car is sold for about 2 to 3 years before that, automotive companies determine what electronics should go in, what software will go in. And then it's frozen after that. The car goes into production, you buy it, an average American owns a car for about 6 years. The lifetime is probably around 12 years. But the electronics are frozen, right? So a lot of cars, trivial things also, like a lot of cars came with your iPhone, the previous generation iPhone plug. And now the iPhone 5 comes out and, okay, got to buy a new car, right? But on a, someone I asked my wife, like, what sort of car do you want? She's like, it should just have the audio jack, right? And that's it. So that's pretty. She's not so demanding. So on a more serious note, right? So if you look at in 2010, there were 20.3 million vehicles recalled, and the fraction of vehicles that are being recalled due to software issues has been growing, and this number is crossing about 13%. And so these are, so an automotive system today would have, say, about between 40 to about 70 microcontrollers, and there's over 100 million lines of code in your car, right? That's more code than Windows XP running in your bucket of bowls. So it's no longer a bucket of bowls now, right? So the more code we have, the more errors that are cropping up in terms of your software issues, and the more recalls are happening, right? So if you look at the some examples, so this is not really to pick on anyway. It's quite across the board. So for example, in 2009, Volvo recalled about 17,000 cars where the fan circuit to cool the engine was not programmed right, and it would shut off at intermittent points even while the car was driving. So the engine would overheat, and so the National Highway Safety Association said that the engine could explode at a point in an extreme case. And so they had to recall all these cars. They essentially are just reprogramming the car, no hardware change. Jaguar, for example, recalled again about 17,000 vehicles in 2011 due to cruise control issues. So this is a software issue with the cruise control, that you put your car in cruise control and you're driving along, and then when you want to get out of cruise control, it just wouldn't come out, right? So you got to pull the handbrake, or so. Luckily, nothing really catastrophic happened, but they had to recall the car. And again, you go to the dealership, they'll pull out that ECU, the electronic controller unit, and they'll put it on the side, and they'll put a whole new one, which really just has the patched code in it, right? So no need to go through a lot of that. So I mean, there are many cases, like Honda had a recall for 2.5 million cars where, if you hit the accelerator pedal too fast, the automatic transmission wouldn't respond. And so you might be stuck in your first gear while revving at, at a high rate at about going to 55 miles per hour over there. So your transmission box could, again, have a big problem there, right? So if you look at what's wrong with the car today, when GM or Ford or Toyota, they sell you a car, the moment it rolls off the dealership, of course, it loses that 20% depreciation, but they also lose, all contact with the car. They don't really know what's going to happen with the car, right? So it's a black box to a large extent with them, unless you go for your, 60-mile, service, or it's a black box to OEMs, the companies that deliver that manufacture the parts and the electronics for the vehicle. They would like to know, what is the performance, and under what conditions are, your vehicle actually, is it breaking down, or is it not performing, or is there a safety hazard? It's a black box to people like you and me who are just owners of, I'd like to know what's the health of the car. I definitely trust my mechanic, but I still like to know, right? So if you look at the way automotive systems are designed today, there is a huge amount of effort, and it is very sophisticated in terms of software and hardware design for these electronic controller units. They are across a several number of buses in the automotive system. But it's all done at design time, right? They model it, they verify it, they do a lot of checking in the pre-production stage. And then they provide a certain fixed number of diagnostic trouble codes. This essentially brings up your check engine light that comes on over there for doing that. So if you have a problem, then it gives you. The problem is that of all the hundreds of diagnostic trouble codes and the 100 million lines of software code that is in the car, there are only 8 codes on that order of only about 8 codes that really look at software issues, right? And they are quite generic, that you have a memory error because you have a CRC check fail. But they don't really tell you what the issue is with your stability controller, or they won't be able to tell the mechanic unless they actually go and really investigate it back at GM or Ford or Toyota. So everything is done, you have a problem, it's going to be very reactive. Unless there is a massive scale recall, things aren't really looked at, because there are warranty management costs related to that. So then the new view is that why don't we actually always have a way to monitor the health of the car? And now obviously we want to really look at the post-market monitoring of the vehicle, where once the vehicle rolls out, if say 50 customers are complaining about a problem, today having a recall for that would be quite ridiculous financially, and so they have to wait for a big breaking point of a few thousands of or tens of thousands of vehicles to be recalled. And so can we now remotely diagnose the car? We can remotely speak to the car, and can we remotely do code updates, which is quite terrifying, but I'll talk a little bit about that. And can we then we have to do this in a very safe sort of manner. So I come from very safety critical systems of like aerospace, medical devices, and so where safety is really the primary concern, performance is well below that. And so how do we do that runtime edge? So here the idea is that we want to have dynamic trouble codes. I don't know what problems I can expect with my software, because it's actually very involved software across the vehicles. They have very involved interactions across the vehicle. So can I dynamically have a way that if a customer complains now of their ABS or the anti-lock braking system, can I send in some code that will start monitoring that? So essentially, we are really trying to have, the car already has a lot of fault diagnostics and isolation within that. So it can switch between, say a high performance controller versus and if there's an error or it's not performing within the stability region, then it can switch to a high assurance controller, and maybe that consumes more gas, but it's still keeping the vehicle safe. So again, to echo what Alan Taub mentioned yesterday, that these systems have to be they should be able to sustain operational failure, but never result in safety issues. So how do we really start thinking about what this remote diagnostic center would do? That we want to remotely analyze the code that's running in the car for a specific type of problem, and then once we get that, we want to be able to sort of now look at a tool chain or look at a way of end-to-end architectures that we can do for monitoring. So at design time over here, the automotive companies and the OEMs already have a lot of models, whether it's in simulating state flow or different tools that are there today, and then the code is generated and tested and verified into the electronic controller units. But now in the post-market time, we want to be able to do runtime diagnostics. So if there is a certain problem with a stability controller, we want to be able to go in and actually talk over the cell phone or talk through your cell phone or talk remote directly to the car over the CAN bus, which connects all the electronic controller units, and be able to start observing the code on that electronic controller unit. And then from that, we can now, at the data center, we can start creating a plant model of your specific vehicle. And I'll get into that a little bit more. Given that, we can reformulate the controller and then design an updated controller so that we don't have to recall the cars. We can do that at nighttime while your car is parked, for example, and do a remote code update. And we're not going to really switch in a new controller right away, so we have to do that, again, very carefully. So I'll just walk through these steps pretty quickly. So essentially, we are really tapping into the guts of the electronic system in the car, and we're really looking at how these controllers, are going to be talking to the remote diagnostic center, how they're going to be, what sort of interface they're going to have to say, well, these are some hooks, and I can monitor certain variables in how the controller is working in software. So if I'm looking at a stability controller, I want to look at the yaw and the roll and the lateral velocity, lateral displacement of the vehicle. To be able to now, I'll be storing and summarizing certain observations of that on board, and then sending these summaries back to the data center. At the data center, I already have the design time models of the car. So I can say I can start matching that to how is it different from how the vehicle was originally designed. Right, so our research focus is at this intersection, at least for automotive systems, of control theory, of how do we actually come up with ways to start remotely monitoring these systems and verifying these controllers once they are reformulated, and also how do we build the mechanisms, right, and these architectures and the protocols to be able to talk to the vehicle in that case. So I'll give you a quick video of one of the things that some of my students had built for fun. So how we can actually look at vehicles over here. So So here we have an automotive, just the guts of couple of electronic controller units of a car. So we have, different electronic controller units for the brake, for the engine. They're all connected by CAN bus. So this is like a toy kind of system, but there's a much more elaborate system over here. And you can even drive the car if, as needed. So this hardware system now is connected to a game engine, right? So we are really looking at, high fidelity vehicle physics over here of this game engine. So the car is completely controlled by, your is completely controlled by the hardware, and we can do real-time monitoring of all the aspects of the car, right? So you can think of it in that that we are always able to monitor the system. So let's look at traction control, right? With traction control off, as the car is taking off and driver's jamming the pedal, there's a lot of wheel slip over there, and the car becomes very unstable. So here you can see that the vehicle is like the accelerator pedal is jammed, and there's a lot of wheel slip that's happening. So now we can turn traction control on, for example, and you can see now we are throttling the accelerator over here, the acceleration of the car, and we have a smooth takeoff. And as there's a variation in the traction, the system is adapting. So here, even though you're jamming the pedal, we are modulating the throttle to minimize the wheel slip of the car, and we're getting all this information in real time from the hardware test bed, right? So this is one of the this started off as one class project, 2 years ago, and it's become a fully funded program now. So anti-lock braking systems, as you jam the brakes is common. You can see that the car starts skidding over there, and so again, there is a lot of wheel slip. And as you would expect, if we turn on, anti-lock brakes over here, so you are going to be pumping the brakes in this case, and the car comes to a gentle, smooth halt, right? So like this, we can look at, many different examples where, we can look at, different controller implementations done at design time. And as the models get more sophisticated, we can start analyzing that in more detail. So there are a lot of problems that occur in the post-market scenario, right? So for example, we are looking at sensor-related faults where there's noise or there's change in suspension parameters. There's a lot of delays and network sampling jitter. And so so these are really the cases that we're interested in the post-market scenario. And so like I mentioned, there are only 8 of these codes that look at the details of software. We're really interested in how we do dynamics of dynamic diagnostics, right? So we're using the model of the car, and then built on that model, we don't have to use heuristics. We can do a structured system identification. That means I can see how the controller works, and I can actually recreate the model just of your car, and then I can design a controller for your modified version of the car, and I try to isolate, well, if this sensor has increased noise, how would the reformulated controller actually work? And so I won't go into details over here, but this is common techniques of how we do the fault isolation to a specific issue. So if I have a problem with a specific controller, say for your roll angle or your yaw rate, then accordingly we can isolate that very easily. So and then once we do the code update, we have to have very safe techniques that how we do this update, right? So the way we do all this is that if you have your traction control code that's running on your electronic controller unit and stability control running on another electronic controller unit, we don't want to interfere with what's going on, but we can send our code in, and that just takes the empty time or the slack available in your operating system and starts running our diagnostics in a very opportunistic manner. So I'll switch to the next level. So we built a lot of these interfaces to talk to the vehicle back and forth. And the students that built a lot of these, they won the World Embedded Programming Competition last year in Korea. And so we'll look at vehicular networks. And this project actually started within GM and while I was at CMU. And so essentially, GM had given us 5 cars. They were very generous. And but we had to drive them all the time. Drive these in Pittsburgh or wherever, and some of the cars would talk over the cellular network, and then here in Warren, they would be able to monitor us driving in the cars over here. So wanted to look at, well, how do we build protocols that if there's an accident on the vehicle here and we're only communicating, so cars have the 75 megahertz of bandwidth that's dedicated just for communication between vehicles and between the vehicle infrastructure. But if you're building these protocols with 5 cars, any protocol will probably work. So we built a tool that can allow us to say that, well, if I have 2 real or 3 real cars, if I want to look at the protocol with hundreds of vehicles, I can just virtualize the other ones in a simulator in the lab. And so the same code is running and the same packets are running from the real car, then it goes to the simulator in the lab, gets virtualized, and then comes back to a real car. So I can switch between the real and virtual. So here I have 5 real cars in Pittsburgh and about 500 or so virtual cars driving around. So I'll show a very quick video of what I mean by what's happening over here. So I can pick any city. So I can pick, say, Boston over here, and I have all these cars are tracked. They are all vehicle-to-vehicle enabled. So this car over here, say, has an accident and sends a message across. So we wanted to really look at, what's the so how does it communicate? And now here this vehicle is going across the Charles River. It gets into range and starts communicating. So we can model all the, a very detailed view of these systems across any US city. And also we want to really look at, well, if 1% or 2% or 3% of the vehicles have this capability, how will it actually make sense from a market point of view? And so those were the questions and the type of protocols we're building, real-time protocols for safety, with the GM lab earlier. So I won't go into the details of how this simulator works, but it's free, it's available, it works with cars, it works with synthetic traffic, and real traffic is coming up. And so we can look at different cities, like this is Chicago, and 10 minutes later, the vehicles, if they're all routed to their own origin destination, they'll start moving to faster roads like normal. How would propagation go across Manhattan? Or if there's an accident, how would a message live within that region for some time, just going from car to car? And so the results were actually very promising. And so we built a lot of systems that plug into the vehicle, so we can actually use a GPS time synchronization where we would get about 20 nanosecond difference between 2 vehicles wired, and then wireless under a couple of milliseconds. So we can build protocols that are very synchronized between vehicles so that we can have pipelining of this messaging across the highway. So I'll go to the last sort of topic over here, which is really looking at now, well, we can look at vehicle to vehicle, vehicle to infrastructure, but what if we really want to look at the whole system now? So if we have, say, a couple of vehicles that are being probed on where they are, what their speed is, and obviously there are a lot of questions related to security and privacy. I'm going to talk about how these systems are built, and there are parallel efforts on those, not necessarily by me. But so here the focus is really on how do I do real-time route assignment, but we want to do this for hundreds of thousands of routes being assigned. So we built this second type of simulator that runs with synthetic and now recently with some real traffic. And I'll show you quick videos of how the system actually works. Okay, if I can find the window. Pardon me, I just lost the window somewhere behind. So here the system is actually, you won't be able to read this text over here in this resolution, but this is Washington, D.C., and we have about 380,000 vehicles. And I'm going to ramp this up to about 800,000 vehicles. So now there's 620,000 vehicles. And you'll see it's getting redder and redder as the congestion is building. Every car is modeled as a thread on an NVIDIA GPU. And they all follow each other. They follow some minimum traffic rules. And so we can model very large-scale congestion. And what we are really interested in over here is, now if you look at the city of Philadelphia, here I have 500,000 cars. So this is a very large simulator that runs very fast also. In the city of Philadelphia, you can't see them. They are specks of red. And so we want to route this one vehicle to, say, downtown. This is the blocked one version is the route that Garmin or Google Maps would give you. But now, based on the every 5-second change in how the traffic is getting congested and congestion is moving, we are determining what's an averaged out, smoothed out 1 mile look ahead of how we would actually drive. And not necessarily in a greedy fashion, but you can see that we are adapting the route every 5 seconds. That's probably not that's too fast a rate to adapt for a driver, but we just wanted to, it's like, go there now, go there. Exactly. But we just wanted to see that we can push the system, right? So we can do this for a very large number of vehicles. Now everyone, say I'm going to the airport, someone else is going to Ann Arbor, they can get all the fastest routes for nationwide in this manner. So I'll just wrap up over here. And so this is so we are applying a lot of these systems to the second version goes to 260 million cars, but I'll hold off on that for now. So we are applying a lot of our work in the city of Philadelphia, where there's a new traffic operations center being set up, and a lot of these tools and algorithms are being incorporated there with the mayor's office as part of this university transportation center. So that just concludes how we're really looking at single vehicle, vehicle to vehicle and infrastructure, and then how we look at a large scale. Obviously, this is a very high level view of it. Thank you.
Thank you, Rahul. We have about 15, 17 minutes for questions.
Nathan Moody, Los Alamos. Excellent talk, by the way, really showing the rigors, I think, of system engineering in play. So I have a question because of the safety aspects of it, the revision of code, and it's very interesting to think about that. But you kind of now have version management problems, right? Because you have version 2.0 of the vehicle. Multiply that times those millions that got modified. Is this really a practical way of managing vehicles? And then also a follow-up question is, bit for bit, can you really verify that the software image was downloaded properly? Because we're going to be trusting an ABS system to that software image. And is there a chance that the communication, some process that you outlined, stochastically could go wrong, and therefore the ABS doesn't actually function?
Right. So both are. I mean, we have a gun to our head when we are dealing with safety critical systems. So let me start off by at least sort of say that this system will that's the end goal of the system. We're not really going to start with safety critical upgrades. It's going to start with like recalls due to simple things like a door window. It would go up to 70%, but the sensor would say it's 100%. In terms of the software being the encoder for the software, so we can reprogram that remotely. So or things like now let's go one level, little bit more interesting, where say like Ford has the Ford Sync, and they had a sort of code upgrade or Windows update for all the Microsoft Sync software that's running. And they had this versioning problem that different cars are running different versions, and the same update would brick some cars, like our chair's car over here. So but I mean that's not to slam Ford. I mean this is a complex. We are working with very complex software, and but now to go to the most safety critical part. So one thing that I glossed over a little was this runtime verification part, which is even in academia it's a very very hard problem. But the idea now is that suppose I have my original controller, which has been downgraded within the car's fault tolerance system from a high performance controller to a high assurance controller. That means it works, but it's suboptimal. That means it might consume more gas, or it might not allow you to steer to the extent that your high performance controller will work. So while the high assurance controller is running and we send in this updated controller, we're not going to say, okay, switch now, trust me, it works. So that would be, for every engineer, there are 12 lawyers to take care of that, right? So obviously we're going to have a way, we have to have a way in which that the updated controller is verified, but it's verified periodically. So that means I want to really explore the state space of where the controller is operating. So when I'm on the highway and it's quite stable, then I can switch to the new controller for, it's called delta execution. That means I'm executing that for a short bit, just testing and getting the verification for a part of the state space. And then as the vehicle, as that state space expands, we will keep sending updates and saying that, okay, now you can expand the bubble. That's one way. It's still very high risk, right? So, and in terms of doing this firmware over the air, so that's kind of like a, I won't say it's a solved problem, but from the, that's more of an engineering, and the industry has very good standards for doing firmware flashing over the air, and these statistical variations will also be checked by doing static analysis on the vehicle system itself and running tests across different execution pathways once we send the code up there. So some bit of what I'm saying is pie in the sky, actually, right? You're not going to be doing heavy-duty, runtime analysis of your code once it's up there, but we can do, very high fidelity checks and timing analysis and, code integrity analysis on board over there. So I would say the biggest problem really is, how do I trust maybe this new controller that we reformulated at the data center works fine, and we tested out maybe on a couple of cars, on the racetrack. But how do I, can I give you 100% guarantee that it'll work with your car, right? So that's a big challenge, and that's not very non-trivial. So that's why Prasad Venkatesh from Ford, 2 years ago, he said, hey, you guys can do that in academia, but we're not going to talk to you for some time. And then this Windows Sync update happened, and and they had to give everyone USB keys to update their car. And then he's like, okay, come on, forget what I said before, let's chat. And he's a nice guy. I mean, he's a good friend of mine. But but that's sort of where the industry is getting to.
Brett McMickle with Honeywell. UAVs, one of the concerns with UAVs in domestic aerospace has been with GPS spoofing as well as spoofing the command and control. It seems like the vehicles have a lot of the same susceptibility. Is there any work being done on the security for vehicle-to-vehicle network?
Yeah, so security and privacy. So if we just talk about security over here, so I'm not a security expert, but there have been some very interesting papers from University of Washington and Illinois on hacking your vehicle, hacking it over Bluetooth, and disabling a lot of the functionality. And so in terms of that, how security attacks are manifested in controls is actually a very interesting problem. And so recently, Penn has been the lead in one of the DARPA programs on high assurance automotive control security. It's called HACCMS. And we just had the kickoff last month. So you can see your questions timing is perfect. But it will take a while. So because you can mask many security problems as a fault. And so you can't use classical fault tolerance methods to decipher if there's a disturbance to your controller, because these disturbances can be so small. And there was a great talk, I think a month and a half ago, on GPS spoofing, where you can just put in very small errors, and your vehicle will start drifting over a few miles, or your stability controller will start destabilizing very slowly. It's totally undetected. So I guess the first wave is really the computer networking, the computer science type of security. Right now, none of this is encrypted. Anything my students, they routinely hack Toyota cars. No one from Toyota, right? So I was telling a couple of folks last night. So because then they would start writing to the car, which is really dangerous and voids the warranty of a zip car. But and many times they would write wrong codes into that, and the car would shut down for like 2 hours, and then it would reboot. So that's why we built our little platform in the lab, and it's grown much more than the video. But yeah, security and how we actually can unmask the security. So as part of this DARPA program, we're actually re-architecting how we would have very specification-based and very formal methods, approaches of designing controllers for automotive systems. So how do we harden them, all the way from design time, and then be able to really look at their fidelity at runtime?
Hi, Lena Singh, Draper Lab. Great talk, by the way. Really interesting. So I wanted to ask you. You had this you had sort of a flow of control slide where you talked about doing onboard system identification and then subsequently sort of reformulate the control gains and so on and so forth and continue with the diagnostics. I imagine loop closure. So fantastic concept, loved it. But here's a question for you. If you bring an operator, if you presumably the controller updates are being done, in some command center somewhere. At that juncture, basically, then, how do you sort of envision realizing this? Because at that juncture, you're sort of looking at, okay, an operator or a controller or an estimation theorist or someone per car. And at that point, then you're replicating what you're seeing with in the UAV world, where the military is complaining about an operator per UAV is getting too much, and now when you're talking about doing this with cars, you almost need the entire population, right? You pretty much basically need to sort of give a control system theory or an engineering degree to the owner, so they can sort of redesign their to update and sort of redesign the control systems for their cars, yeah?
So the comparison to the UAV is quite different. So in the UAV case, at least to my understanding, they are operating the UAV remotely, and they're really they have to have some secondary eyes and ears for the UAV system, especially when they are doing some sort of actuation related system detonating or. So, but in an automotive system, we have our design time models, and so the human in the loop comes in when the customers come in and say, well, we have this, we are detecting this sort of problem, and it's in English and it's in customer language. That has to be translated to what the engineers will map onto, saying, okay, seems like they have a problem with stability and maybe some aspect of, say, traction control.
So this is not proactive. This is really after a complaint is registered. Is that what you're saying?
Yeah. So we're not always monitoring all the cars, because that would it could be down the line that you're always doing that. But the point is that all this tracking, once the hooks the diagnostic codes are sent in, all that can be very automated because we know what we are looking at. We are really looking at the residuals or the difference in the control behavior between what your car is demonstrating and what the model, given how roughly or how smoothly or what sort of driving behavior. So whatever inputs you're giving to your car, we'll feed that to our model, and then we'll start looking at the differences in the behavior. So that's all automated. Even in our lab right now, it's all automated. So we don't have to. The system identification is very structured because we have a model of how the original system was designed to behave. So we're really looking at what's the departure from that. All problems are not going to be that straightforward, but we're really focusing on those easier examples or relatively easier examples first.
If you have the capability there, it seems to me that you could do this almost on a continuous basis, really. I mean, frankly, rather than, a fault has occurred.
Yeah, but we should know what we are looking for, right? And there is a cost of communicating to the cars. Cellular bandwidth is actually very expensive compared to what we get at home. But I mean, so I guess disregarding some of these, secondary reality effects, yes, you can always be monitoring the car. You can proactively find issues, but it's hard to decipher them unless we have some context. And the context is really afforded by the customer giving a complaint or really post-mortem analysis from a traffic or from an incident.
Yeah, Dave Garrett from Broadcom. So the question I had is on the traffic simulation where you're routing, millions of vehicles. And so everyone's trying to go downtown at rush hour. Do you see any insights like you make some people lose and some people win in cases? And
yeah.
I mean, what happens when the case the router is screwing with you and you ignore it? I mean, what's the psychology behind?
Yeah. So that's like this. I think so. There's this. I call this the tension between the tragedy of commons and price of anarchy, right? So that's always going to be an issue, and that is a very general network problem. And so if I tell everyone, hey, that's a faster route, like whenever I go to New York from Philly, they always say like upper level of George Washington Bridge is 6 minutes, the other is like 16 minutes, and nobody goes up because they're all like, hey, we are smarter than the rest. And then the lower one is actually faster, right? So trust actually gets degraded from that system also. So there's non-compliance effects. And there's oscillation effects in the extreme case, right? So we can introduce non-compliance. And then there are problems of coverage. Suppose I have a lot of vehicles going through the main arterial roads and the highways, but what if I want to explore what's the current speed now along these other routes? So I have to punish, it's 5% of the folks, but while doing a min-max optimization of that the worst case pain that they have. So it's not a new problem. It's just that it's becoming very apparent in a very more dynamic environment over here.
As long as it's not me, I'm okay with it.
Yeah. So we'll charge you $5 more per month. Yeah.
David Brumley, Carnegie Mellon. So this is just a comment because I saw it last night as well. I think any security person would say GPS is an inappropriate protocol to use alone. It's completely unauthenticated, and for $2,000, you can create your own virtual GPS satellite, and with a 1-watt transmitter, manipulate everyone in a 60-mile radius. So clearly there's more engineering challenges beyond just the vehicle thing. We actually have to put up authenticated navigation networks. The DoD has one, but currently you have to have security clearance to even access it. So, yep, just a comment.
I had another question about routing. On the internet, there have been some surprising results that selfish routing works much better than you might think. And just as a follow-on to the previous question, how bad is selfish routing for cars?
So I mean, we are always selfish routing today because we're just, and even if I have to, so I mean the taxi ride from the airport till here took longer than my flight till Detroit, right? So I mean, it depends. So there are problems with it depends on the topology, right? So here we have 1 or 2 major routes to come till Warren from the airport. In DC, you have quite a few major routes, and then people automatically decide. And so we have many examples of at 6 a.m. this is the shortest path and the fastest path, and then by 7:30 when it's peak hour, how the fastest paths keep changing. And if we were just to look at one car's health and everyone else is just for doing selfish routing. So it depends a lot on so one problem is can I look at a city and analyze the topology of the city and the throughputs of the city routes and then figure out how much diversity I have, so that what would be alternate routing paths that even if you're selfish you might still balance the system back by that. So and then there are all these Bayes paradoxes, that if we sort of put like lower weights on certain links, then they actually are very destructive. So at some point, this is a very dynamical system, and it really tips over very fast and takes very long to recover then. So, but that's a very open problem, I would say, that how do we analyze different topologies and say, well, under this case, this is the best we can do. And so in DC's case, it's very hard to improve on that, just because there's only this one beltway and everyone switches to that very quickly in the morning.
Do you have any information about privacy concerns, especially about crashes? I don't think many people would want a central computer to know when their car crashes.
Yeah, so I would direct that to the David and the Scilab folks. So privacy is always at tension, at odds with what we are building, and so I would say it's very complementary. It has to be an integrated part, but I per se don't look at the privacy aspects. But there's been some remarkable work done both at CMU and Berkeley, where they actually where they have defined like virtual routes where it doesn't track you all the way to your home. It doesn't track you beyond. Only certain segments are mapped, and so for all this work, we don't really care, what you're doing, where you're going. I mean, except for this part over here. For these two parts, we don't really care, what you're doing with your car, where you're going. I mean, there are privacy concerns with today's Easy Pass toll system, right? They've come up in divorce cases that, they knew this guy was doing something in that part of town, right? So these are, I would say, they are beyond the scope of looking at just the controls and building of these systems. But without those, none of this will see the light of day. So that's part of this collaboration that we have both with the University Transportation Center and the folks at CMU and this DARPA high confidence secure control systems is really to start addressing those. And there are people far smarter than me on those topics, like Adrian Perrig, who has looked at this for a long time.
Okay, we're out of time for questions, so let's thank Rahul again for a very interesting presentation.